Good morning, good afternoon, good evening. My name is Srinivasan Venkataramanan, shortly Srini, and my good friend Balram would actually be delivering this at the LatchUp 2023 at Santa Barbara on April 1st, 2023. We first of all want to thank the FOSSI Foundation for giving us this opportunity to share our experience of running a system Verilog assertion based checker IP in open source simulator that is Verilator. Quick shout out to all the sponsors for making this happen, including Antmicro, Google, Zero, eFabless, and Open Hardware. Thank you all. And I represent this company called AsFigo Technologies, which is UK-based startup, and that's our website www.asfigo.com. So this here is the agenda. It may look crowded, sorry about that, but essentially what I'm trying to communicate to you is we'll start with an introduction, we're just doing, and then we will set a play area as to what we're trying to achieve in this particular talk, including the assertions, what the simulators, that's Verilator, and a unit test framework such as SV unit, and the case study that we are going to use is AMBA protocols because that's quite popular in the industry. And the main message that we are trying to communicate here is for a standard protocol such as AMBA Peripheral Pass, APB, or AHP Lite, we could actually write a bunch of assertions and test them completely using open source tools such as Verilator, including a good framework such as SV unit and bit of UVM2. That's kind of our intention, and we'll describe our approach as to how we went about it, and then we will duly acknowledge the contributions from various people, and we will also list the kind of issues we have found and what we have managed to fix so far. So we will definitely include the Verilator, Google's variable parser, which we use it as a parser as well as a linter and a formatter. And we will also show good amount of SV unit, and we will also show the kind of porting we did to run SV unit on Verilator. And a last minute entry, which is a surprise entry in this presentation, is called waveterm. A good friend named Peter came up with this idea of debugging waveforms in a terminal. I'm sure there are many other ways to explain this, and I'll let that evolve over a period of time. Since I found it really nice, I'm going to include a screenshot of what I felt so good about including it in this presentation. And I'll conclude that with one slide on how I see open source and why open source, or many people ask me, why are you doing what you're doing? And I'll conclude with that. Thank you. So here is a brief note on what AsFigo is. As I mentioned, we are a UK-based chip design startup. We bring decades of chip design and EDA expertise. I personally have worked at Synopsys in the past, as well as I've done more than 15 different tapeouts for various employers as well as my customers in the past 22, 23 years. And we also, to the UK audience, we bring a globally reputed training solution, including the RTL design verification, various languages, and primarily we want to work on this bringing AI ML to chip design flows, including the generative AI and AI analytics. These are things that we have done in the past, though we did not really name them or brand them under this umbrella of AI. And given that that's becoming the buzzword, we're just kind of looking at how we could leverage on the work that has been done in the past to add value to chip design flows. Thank you. So quickly, what does AsFigo do? We are primarily focused in bringing artificial intelligence and machine learning into chip design verification flows. And there are few thoughts on how we want to achieve this, including various training sessions that triggers the young minds to do this even better, including the ones that we could, for example, imagine that use augmented libraries on top of UVM to collect more data, and use vendor-specific APIs to query more information. That could be on Python, for example. And we do train a lot of engineers in doing these things in various forms. We also develop various EDA flows to enable this, and we are very focused on leveraging on open source solutions that are out there to make it a lot more acceptable and adoptable in the industry. So our playfield for today would be centered around assertions that you see on the right hand side of this particular slide. Many of you would recall system Verilog includes good temporal language called the assertion subset that includes the famous event ordering over there, including your preponed region, your active region, your observed region, and postponed region, and so on and so forth. And we have a lot of material on this, including several books that I personally have co-authored. You're welcome to try out those. And primarily, we are taking a specific case study of AMBA bus, both APB and AHB, and we're going to run these assertions using the open source simulator named Verilator. In case you haven't got to it, please do Google it, or verilator.org, or you can find them on the GitHub. Please do download and try it out. It's fantastic. I highly recommend. And we also leverage on an open source unit testing framework developed by Neil Johnson and today being maintained by Tudor. So that's called SV unit. A new chance to lead. I really believe that because it's really fantastic for a targeted application, specifically such as assertions and functional coverage and things like that. It's also fantastic to use it for drivers, UVM monitors, could be for scoreboards, etc. There are very many ways that unit testing can be of use to commercial design houses. That's kind of what we are trying to achieve today, saying we will write assertions for specific AMBA bus protocols and run them on Verilator and test these assertions using unit testing. We will also have a surprise entry. I'll talk about that a little later. And of course, all of this is completely open source. There's nothing that you got to pay for. So starting with APB, AMBA Peripheral Pass. Most of you are familiar with it. There's a P address, there's a P write, there's P cell, P enables, and etc. And of course, these assertions are already listed, and this list is already available on the public domain. We also have it in the Git repo that I'm going to show you. So it's I'm not going to go to the list of each of them because it's the font size is too less, and it's also probably not the best usage of your time. But primarily, let's just take a quick example of P cell to enable. So we see that the P cell at clock T1 has gone high technically on T2, and at T3 you would expect the enable to go high. If let's say the enable didn't go high on T3, that's a failure. And that's kind of what the assertion looks like. And of course, there are very many requirements. There are about 15 or 16 requirements that we have listed over there. And by no means it's intended to be exhaustive or comprehensive. We don't warranty anything. It's open source. You can take it, tweak it as it fits your requirements. Similarly, continuing for AHB Lite, we have come up with more than 25 assertions over there. Again, of course, it's a little bit more complex protocol, so you would expect more assertions for a protocol such as AHB Lite. Again, this list by itself is going to be available on the public domain on our GitHub. So what's our approach? The approach is to take these requirements and code them using standard system Verilog assertions. When I say standard, it's standard as in the IEEE 1800. However, we do restrict ourselves to the subset that's supported by Verilator. This code was already developed in the past for a few customers, and it's been running in commercial simulators, and it's been used for a wide variety of design verification projects. When we wanted to use it with Verilator, we got to tweak it to the subset supported by Verilator. And one of the major things that you would find when you're trying to do this on your own designs would be the lack of sequences, for example. The sequence end sequence is something that today does not run on Verilator, And my last slide in this presentation would request you all to pitch in if you can to add these supports. Anyway, so one is to begin with the coding the assertions. Starting with the specification, we have a list of requirements. Let's code the assertions. Make sure they are Verilator friendly, and we have these great examples out there. Again, that's part of the Git repo that I'm going to show you. Once we write assertions, what's next? I heard recently a presenter talking about value of unit testing for assertion, and I found it really, really good. The way he put it, it can go wrong by a single clock. And do you want to write a complete UVM bench to verify that assertions, or verify that assertion, or large design, you really want to spend a lot of cycles debugging a single clock? Right? It could happen. We're not saying it won't happen, but let's make sure the assertion model by itself is robust. To do that, what we felt is writing unit tests per assertion is a fantastic idea. And it's much easier to test. You don't have the big time phases coming in, trying to say, okay, here is a TLM port connected, did you connect it, did you not connect it, did you get a let's say a data type compatibility errors, blah blah blah. Right now, instead, let's just start with the unit test. In fact, at least there will be 2 unit tests per assertion. One is for a pass, other is for a failure, because we want to make sure if there is a failure on a specific requirement, the assertion better catch it, because this is called verify thy verifier. Somebody has to verify your verifier as well. That's really what a unit test could do, especially on a failed unit test. And we use SVUnit. There's no reason why we cannot use other platforms such as VUnit, but just that we found SVUnit a lot more easier to work, especially with Verilator. And of course, we had to do a lot of porting. We'll talk about some of that as we go along. And once you code all of this, of course, you got to run and debug. And this is something that's a lot of fun, especially in open source world. Things don't always work the way you would expect, especially from coming from a commercial simulator background. You got to have that, kind of engineering kick to do this. And that's what we really found nice. And sometimes you debug using VCDs, the GTK waves. That's something that you can. And we did find few issues around it, so I'm not going to talk too much about the GTK wave integration here, but it's certainly a flow that works. We do have that enabled in the repo. What we also introduced is something called SV wave term. Sorry, there's a typo there. I'll fix that. SV wave term is nothing but a log-based wave tracing. It's being promoted or developed by Peter Monson. And I strongly recommend you go and check out. This is a very, very new development. So I certainly request, please go to the GitHub repo over there and try it out. So let's start with a sample APB assertion. So here is the requirement over there. The FSM can stay in active state for exactly 1 clock. What that means is, as soon as you are in an access state, the next state has to be either a setup or an idle state. Right? And if not, we go and print an error. So a couple of things about what works very well in Verilator in terms of SVA. This is a standard SVA code. You see that there is a label, there's an assert property, so that essentially tells you that concurrent assertions do run. And we have used default clocking, hence the clock is not explicitly mentioned. That also tells you that the default clocking really works in Verilator. We talk about the abort condition, the disable FF, and then there's an antecedent and a consequent, as you would imagine. Again, just to show you that a good standard temporal expression does today run using Verilator. And we also have a nice fail action block that could react to your failures. So things like, for example, you want to print a UVM error, you want to count it, you want to stop on a first error, so on and so forth. You could do whatever you want to do. And we're also going to show you how we could leverage on the fail action block to integrate this thing called the wave tone, for example, to debug things better. So once we do have the assertions coded, how do we test it? Again, as I mentioned, it makes no sense to throw out a bunch of assertions on a large design with a UVM bench in a subsystem and then go and debug it for hours and come back and say, hey, this assertion, there was a #1 missing or something like that. You don't want to be playing with the unstable assertions on a large database, because typically it could take, let's say, 30 minutes to compile elab and then bring up your waveform using Wordy, whatever, right? And then realize that, hey, you missed a double hash one somewhere. So instead, we strongly recommend write unit tests. And here is how a unit test typically would look for the same APV thing that we are talking about. And here the focus is going to be on PCell and P-enable. Please watch out that waveform. So a simple assertion could be as simple as this: PCell ANDed with not of P-enable, which basically talks about the first clock where the PCell is high and the P-enable is low. The next clock, we expect the P-enable to be high. This is a standard requirement. Now, to test it, you got to, of course, drive. And again, in unit tests, you have no DAT, nothing. I mean, it's just a dummy DAT, and these signals are declared, so you can drive them the way you want, right? You don't have a big UVM sequence or a test and things like that. You don't need all of this, right? So we just use unit test framework. That's SV unit again. So here in this particular screenshot, I'm just showing you a failed trace or a failed test. Of course, we have a pass test that's already checked into the database. You can take a look. So what do we mean by a failed test? To begin with, we say that PCell is 1. The next clock, we will drive the P-enable to 0. And we would expect the assertion to fail. Because if the assertion doesn't fail, your verifier by itself is wrong. So that's what we are trying to do it here. So to see the tick SV test, that's kind of marking the beginning of a test in SV unit. And we named it aptly as fail underscore that particular assertion. And the highlighted one kind of shows you that we intentionally drive the P-enable to 0 1 clock after PCell, which is a violation of the protocol. And our expectation would be that this test should fail and our assertion should kick in and throw a UVM error, technically speaking. And that's precisely what has happened. And looking at again the waveform quickly, you see that there's a log. In the log itself, you get a nice trace of PCell being high at a clock. If you can see it, the P-enable is staying low all along. And with waveform, you don't have to dump things. You just have to enable it in the code. And as soon as you do it, your log file will show you, you know what, the PCell went high on a specific clock, and the next clock P-enable didn't go high. And you kind of have a very quick idea of why this is failing. Of course, you could do a lot more debug in detail if you want, using waveform, driver tracing, etc. to that. So continuing that story, this is our unit test suite that we developed. There are many of them. So in this specific example, I'm just showing you there are 16 tests that we developed for various assertions listed over there. For 8 assertions, we have 16 tests because please recall that there is a pass test and a fail test per assertion. Hence, so for 8 properties, we have 16 tests, 1 pass and 1 fail. Right, and you see that nice reports coming out of unit tests. Again, this is something a lot of you in open source world are familiar with. To say that, you know, we could do let's say the unit tests for things that are small in size, and that's exactly what is happening over here. So our primary contributions, the various GitHub repos. So again, our play area has included Verilator, SV unit. We also use Variable from Google. And we found a lot of these subtle issues that we reported. And thanks to the contributors, we have many fixes, including I myself have fixed at least one issue on Verilator. And of course, there are various projects that we have used, including SV Wavetome. And over here, you do see the right name of the repo. We ported this checker IP to Verilator. And few workarounds added. We have reported more than 10 issues, fixed one inside the Verilator source code, which I'm quite happy about. It's a very small fix, but nevertheless, it's a good start. And we also ported SV unit, and we have few issues open. We have a specific branch with a pull request pending. I will work with Neil and Tudor to make sure we integrate that eventually into the main SV unit because this is an interesting contribution, I believe personally, to run it on Verilator. And we also ported SV Wavetome, again, very subtle fixes that Peter is reviewing it as we speak. And on the right hand side, you see these various reports, various issues. Some are open, some are fixed. Again, all of this is in public domain. You can go and look. So let me conclude this presentation with what do we mean by open source and why are we doing this? And many a times we get this question from good friends around the world. Hey, why are you spending time on open source? What's in it for you, right? And I want to go back to my roots, where I come from. I come from a beautiful state called Tamil Nadu. It's not Tamil Nadu, it's Tamil Nadu. It's a specific one from India. And that's where I grew up. And we grew up learning this great poet. He's also a great freedom fighter named Subramanya Bharati. And he wrote many poems. And one of them that I kind of go through many a times in my mind is to say that in Tamil, it's on the left hand side, you see the Tamil, and that's a photo of that great poet. He was very short lived, but he's done extremely high contributions to the broader world. And what he says, and I'm going to say it in Tamil and then come back and do it in English. Pardon me for this. I'm hoping you will take it in a light vein. He says the following: Vallamai Tharayo இந்த மாநிலம் பயனுற வாழ்வதற்கே சொல்லடி சிவசக்தி. So what that really means is he prays to Goddess to say, won't you give me the strength for me to live a life fruitful to this land? I'll repeat that. Won't you give me the strength for me to live a life fruitful to this land? And to me, that's personally what FOSSI is all about. When you do things in open source, you kind of open the world for many others to benefit from these very small things that you believe you're contributing. Who knows, this could be used for learning purposes, this could be used for further developments, even chip designs, big time folks. And I'm very happy to see, for example, the FOSSI doing this now, a focused effort on the hardware side. We all know the GCCs, the Pythons and all that. So why not in our hardware design world? Specifically, again, I'm going to insist saying Verilator and SV unit rocks today. We are working on a lot more. Hope that you would stay tuned and see further updates. What we did essentially in this presentation is we proved that the open source is now ready for prime time design verification. All our code will be available as open source and continue to remain so via this GitHub repo specifically. And we're definitely looking for more volunteers to help tune the Verilator and improve the support, etc. And please do mail me via svenka3@gmail.com. Thank you very much. My friend Balram will take questions as we speak now.